Hello everyone, my name is Yuheng. Thanks for listening my talk. I will be presenting our work, Automatic Generation of Malware Threat Intelligence from Unstructured Malware Traces. Let's go into detail of this paper. First, I will give a brief introduction to the Cyber Threat Intelligence, CTI for short. CTI is information about threats and threat actors that helps mitigate harmful events in cyberspace. It is now playing more and more important roles in adapting to the rapidly evolving cyber attacks and malware. According to SANS CTI survey, near 85% of respondents indicated that they currently had a CTI program in place. In these security industries, CTI will facilitate threat detection, threat prevention, threat response, and threat mitigation. We think that in the combat of malware, the reporting of the results is as important as the result itself. However, various techniques have been developed for improving malware detection and analysis, but not for the reporting. Traditional CTI generation method heavily depends on security analysts' experience, which is labor-consuming. Nowadays, there is extensive research on machine learning-based CTI generation methods, but many of them try to extract CTI, an indicator of compromise, IOC for short, from online security articles and well-written malware reports. In most real-world cases, however, we only had a large number of raw malware samples, and the methodology of generating CTI or IOC directly from raw malware traces has not been well developed. To address this problem, we proposed a practical method to automatically generate IOC and CTI from unstructured malware traces. This image illustrates how our system works. For one kind of malware, we first use a sandbox to obtain raw malware traces. After raw traces data preprocessing, we build an expression candidate list for this malware family and generate an IOC from the candidate list. Finally, we used other useful information in malware traces and generate the IOC to organize a CTI report following STIX standard. In the malware analysis phase, we use a sandbox to obtain raw malware traces. Those sandbox cannot simulate all the running conditions of malware samples. The information we get from the sandbox report is enough to extract malware features. In the sandbox simulation, the analyzer machine runs only one malware sample at the same time to avoid interference, and the running report will be written in the JSON format file. It is worth noting that the structure and content of the sandbox report will not influence our system and results. There are two kinds of information in the malware traces: static analysis results and dynamic analysis results. The static analysis results include basic file information like file name, file hash value, YARA matching results, and strings obtained from reverse engineering. The dynamic analysis results include logs of interaction between malware and host, network traces, process creation behavior, file creation and delete behavior, for example. We think that not all of them are useful for IOC generation. For example, most of the strings from reverse engineering are hard to understand and meaningless. Besides, not all the analysis results have the same value. For example, file hash value is undoubtedly efficient and accurate in malware detection, but it is trivial for an attacker to bypass this indicator. To generate an understandable and robust IOC, we discard those useless and low-value analysis results in the data pre-processing phase. After data pre-processing, we obtain a shorter version of malware traces, leaving only strings that can better characterize the behaviors or features of malware. In order to generate structured IOC, we first transform strings and samples analysis results into IOC expression. We design the conversion rules between the description in malware traces and indicator item in the open IOC standard. For every analysis results in malware traces, we search the corresponding indicator item, and then use its content to fill the value field. Here are some examples of the transformation. There are also some descriptions in malware traces that cannot be expressed with only one simple indicator item. In this case, we find out all the corresponding indicator item and use AND to connect these IOC expressions. For a specific type of malware, we build a candidate list which gathering all the IOC expressions extracted from malware traces. IOC expressions will be stored in a 6-dimension tube which contains logical predicate, indicator type, indicator subdivision type, expression value type, expression value, and its occurrence frequency. The constructed candidate list can facilitate the classification and matching of IOC expression. For those highly similar IOC expressions, we use a regular expression to merge them. Here's an example. Malware belongs to one string may write data into other process, but the target process may not exactly the same. This will result in 2 different IOC expressions after our data pre-processing. However, the 2 expressions are representing the same kind of behavior. In this case, we use a simple regular expression to replace the target process name. Now we have a candidate expressions list for the specific type of malware. The next step is generating IOC from the candidate list. Our goal here is to select an IOC subset from the candidate list, which has the best precision performance in malware classification. IOC subset selection is similar to the feature selection problem. We can easily evaluate one specific IOC subset, but we may need to test all the combinations to find the best one. We design a heuristic IOC selection algorithm to address this problem. We first add the expression with the highest frequency into our subset, and then continuously add expressions that can improve IOC's performance. The algorithm stops when the number of the expressions in the IOC subset hit the prescribed maximum expression number, or the performance of IOC subset is good enough. The selected expressions will be connected with OR. In the last phase, we construct a CTI report following stick standard, using generated IOC and other useful information in malware traces. we select 6 STIX domain objects, SDO for short, for our scenario, including indicator, observed data, malware, threat actor, intrusion set, and report. We fill each SDOs following predefined transform rules. Here is an example of how we transform a XML format OpenIOC expression into STIX indicator object. We also define 5 kinds of STIX relationship objects to describe the relationship between different SDOs. Here, we give a visualized STIX report of documents. To evaluate our IOC generation method, we used a honeypot system to collect 5 types of malware samples from the internet. We use 80% of the malware sample to build candidate list and generate IOC for each type of malware, and use the rest of malware samples as the test set. Here is the generated IOC for document family, which has 3 IOC expressions, as we mentioned before. For the IOC expression generated from one analysis result, we use AND to connect them, and we use OR to connect all of the 3 expressions. Here are the performance of generating IOC, which respects to the number of IOC expressions. The more expressions we added, the higher accuracy on training set and recall rate on test set we achieve. However, more expressions may not bring higher precision on test sets, since larger IOC will bring more false positive. Not all the malware samples will have dynamic behavior during the sandbox simulation due to the imperfection of the sandbox running mechanism. For these malware samples, there will be very few useful strings in sandbox report, and thus lead to bad algorithm performance. We find that nearly all of the GAFJIT samples in our experiment are inactive during the sample simulation. As a result, we get a rosy curve for it. According to our experiment result, if we set the maximum expressions number to 3, we can get consistent and effective IOC. In 3 expressions IOC cases, the average precision on the test set is about 88%, and the average recall rate on the test set is about 89%. In conclusion, we developed a practical methodology to automatically generate structured IOC and CTI directly from unstructured malware traces. Also, we studied the malware analysis report and defined rules for the transformation between analysis results and IOC expression. To generate consistent and robust IOC, we propose an effective IOC generation algorithm, and we achieve a record rate of 89% on real-world malware dataset. What's more, we introduced the method to generate CTI following STIX standard using information from malware traces. Thanks for listening. If you had any questions about our work, contact us at this email